It's my honor to be here and something with you. I think from that thing will take 5 hours train. So I arrived yesterday. We leave at dark p.m. today. So very soon. So I don't want to write. Simply, I came originally from China, northeastern part. And then I lived overseas for more than 30 years. So my home now located in Melbourne, Australia. Now, for some reason, I dreamed, and I came back. That's, I think, six years ago. So now I'm working as a professor and leading research in industry AI at Qingdao University of Science Technology. So today, I will share something about this stochastic configuration network. So as a core support to develop this industry AI. Okay. First of all, I think I need to just let you know my philosophy in doing my research. So here is some, I think, a very good philosophy from Marcus. So that's everything we hear is opinion, but not a facts. So everything we see is a perspective rather than truth. I think it is applicable to academic research because we have so many fake or weak. So in academic studies, so for example, deep learning, everyone broadcast, promote deep learning, large scale language model that everyone use, right? Very popular. Do you think that's all? I don't think so, at least to myself. I think we have so many demands from industry, manufacturing, so intelligent system we need to develop, especially in China. So we have a big block, right? As you can tell, in this, I think in the past decades, China is moving forward very quick, rapidly. Okay, especially for AI area. Okay, but this year, I think from central governments of China, so they have very clear mind and direction. They want to move towards industry, manufacturing AI. Okay, so that's the background today I can share with you. So talk outlines motivation and the reason behind this industry AI. And then issues in MLP, so MLP multi-layer perception or deep learning models with bifurcation learning. And then I will let you know, open your mind. So what's the pitfalls in randomized learning? Okay, because we have so many publications around the world, but all of these publications, they suffer something wrong. Okay, at least philosophy or technologically, I don't think that's right. So I will share what's my solution today. So introduction to stochastic configuration network, and then in the end, I will express my perspectives towards for the solution in the future. So that's what I'm going to share with you. Okay. Behind the research, especially in the area of industry AI, we have so many interesting algorithms in machine learning. But which algorithm really can solve the problem raised from industry? That's a very good question, right? So in industry, we have so much demands, okay, beyond these current well-known machine learning techniques. For example, in the world, 99%, even more, people, they simply consider backpropagation is the only way to train neural nets. Do you think so? Right? Including deep model. What deep learning simply just for feature extraction from the data and nothing else. Do you think that's really deep learning can help in solving industry problem? Okay, let's go to see, have a look. So for industry application, the fundamental things we still, on our hands, is quite a few, not too much, not strong enough. So to ensure industry security of intelligent manufacturing, we need to overcome some bottleneck. That's no choice, okay? Especially in the area of data modeling. For example, data predictive analytics. Everyone talking about this. The reason behind this predictive stuff is we need to design controller based on predictive values. So the model is very important, okay? Now the major flaws. So I just gave you a list. I prepared my mind last night, okay? I don't think I need to go through reading by reading all these words, but I just gave you the items, okay? First, slow learning speed. What does it mean? You can't expect, let's train a neural nets or update the parameter of the learning model with hours time. That's impossible. For real industry process, no stop, okay? It's time streamline. Keep going, take a control action, we have something as output. So this process, nobody can stop. Once the system got started, right? So if you are training algorithm, your modeling tools is not capable to update or to do self-organizing modeling. What does it mean? That means your tools already failed in modeling task, right? So this is quite important. I do think now we have a very speedy learning algorithm on hands. People keep talking about large language model, maybe training the model, you spent half a year time. Hey, so that's not good. And I think unstable and unreliable models. So that's what even Turkey, my lifetime friends. So we work together how to solve this problem. Unstable. I will show you an example, numerical example very soon. So why we concern too much about this stability when we build a learning model, right? The learning model built based on the data sets is not really reliable. What does it mean? You can predict the value, but the value can be far away from the true one, okay? So this is something related to this, the learning capability and generalization capability. So that's what people working in AI is always dream to estimate the upper bounds of the generalization capability. And then always to understand the capability of predictability, we need to first of all understand if the model has the power to learn from the examples. Okay? So, SF, without learning guaranteed. So, do you think we can expect the generalization capability? That's impossible. Okay? And the third, overly sensitive to hypermeter citing. So, one way you play the tools of deep learning, or even you design architecture of deep models, first of all, you need to understand what's the parameter you want to set. Right? So this is quite deeper. You and I think I asked myself 1,000 times how to define. As editor of these journals, I ask the authors this question: can you understand how you design the architecture? So that's basically talking about not only learning rates, talking about architecture citing. Okay, so this is very sensitive. If you change these parameters in your design, then your model can perform very differently. Okay, so this, I will show you example. The initial weights citing will play very key role for your set size. Okay, the fourth, model complexity and expensive implementation in hardware. So if you're talking about someone very proud of their self, probably they report the result in so-called top-tier conference journals. They're talking about, oh, okay, I got 0.1% improvements. I'm a hero in the world. That's a bullshit, to be honest. Okay, that's misleading to the world. I don't think so. Okay, take your much energy and costly, you get something as a 0.1% improvements, and you feel yourself proudly. Totally wrong direction. Okay, so we need to find a feasible solution with low-level model complexity and a little cheaper implementation in hardware. So that's industry needs, rather than just play the words, okay, in the world. Now, the ability to meet real-time requirements. So all these, I think for industry, as I explained to you, we need very speedy response from the model, okay? So we need a very good algorithm to train the model to update the parameter of the models in real time. So the next, interpretability and explainability, so that's called XAI, right? Ivan still working in the topic. So here, I think people feel sometimes a little bit confused. Interpretability means so computing units, how you can understand it works, but how, why it works. So that means we want to understand why the computing units, we need to design that way and how it works as a whole, right? Let's talk about the model computing units. And then we need to understand the reason behind the output results. So that's explainability. So this, so far, we are talking too much about this black box. So black box model trained from backpropagation, whatever the architecture it is, how many layers it is, but you can't explain. You can't tell why it works, why it fails. Okay, nobody can tell. I think very few. That's why some people working as a researcher, academic in machine learning, they try to explain to explore these kind of things. We make a decision. So decision-making process. If we make a decision based on the results, output, but without explanation ability, then I think the people will doubt about this, the rational, why you make a scientific decision. For example, some faults happen. You don't know what's the fault. We have so many different factors behind this faulty. Which one result this? If we understand, then we can find a way to replace the parts. Otherwise, what we are doing, right? Finally, I think productive output doesn't conform to physical law. That's what these days I'm quite focused area. I think in machine learning so far, this is not the first time I'm talking about this topic. Even in Moscow, I still mention this. I think this is an extremely important issue. Okay, so your output from model doesn't really fit or comfort with the physical law. Do you think this industry will buy your stuff? Forget it. Impossible. Okay. Even you get accuracy, predictive accuracy a little bit higher, you can please yourself, but not industry. Okay, trust me, that's impossible. Because people, you just read your result, and then they can find doesn't fit the physical law. So that means people has no safety concepts in mind. Okay, so many in that scenarios, that's traditional AI doesn't work. So far, at least with the best of my knowledge, I don't think any algorithm from the world, so they can claim the output from the model always fits to the physical law. That's why my very close friend from University of Alberta, the Vito Pedrots, so we discussed this issue a lot in the past. So he published a seminal research publication in cybernetics, transaction cybernetics. If you are interested, you can have a look. At least the philosophy level, so people want to find a solution. How to use knowledge. You already heard the physics-informed neural nets, but that's the only starting point, not the end. Okay. So we are still left far away from the point, the solution. Okay. So we need very smart fellows from both campus and industry partners to work out a solution for this. So I believe in the near future, future years, I think it's a very promising direction in AI, especially industry AI. I truly believe. Okay. So I think I gave you some idea about industry AI, what the industry AI demands. So what's the problem we are facing now? Okay, so that's my starting point for today's lecture. Okay, now let's turn to talk about issues raised from the MLP with the propagation learning algorithm. So what it is? This is something important in history of AI development, and then really promote the AI for problem solving to many domains. But now, I think since the publication in Nature in 1986, learning representation by propagation era, I think, lead the world crazy. Everyone only know propagation for training neural nets, nothing else. Do you think that's a good or bad? And people can receive a Nobel Award because of this. So that's a lot of disputation about this. Now, that's not my business talking about this, but let's talk about the issue, right? So this propagation, we have inputs, we have different header layers, and then we pass the information through the model and then get output, right? And then we have error, reference, target with the target. We try to optimize the parameter. So here we refer to them as weights, right? Try to optimize these weights of the model. Now, famous algorithm by propagation. Now, before maybe guide them, disclose the weakness of this propagation, let's ask you think something else first, okay? Given architecture and the data sets, do you think the model, whatever you tune the parameters of the model can do a good job? Think ability will be satisfied. In other words, the error for the learning will be smaller enough. That's a big professor nodded the head. Impossible. So that's what we discovered. I talked to Ivan a lot. We good to show them to the world, okay, one day. So theoretically fundamental understanding about neural nets, about the learning, I think, far away. Not good enough. That's the problem. So we have so many issues. That's why I keep asking myself why we need to apply this propagation in training neural nets. What's the reason? Do you think that's rationality strong enough? Now, so people can tell me, can say, okay, person one, because we understand this one hidden layer neural nets, they have expression capability. That means universal approximation power, nonlinear continuous function. So that's the people keep talking. Well, because this, and we promote, we are using propagation. Don't forget, that result is only existence result rather than in design. Just like something people quote, you do this, do that, then you will go to the heaven. Do you think that's true? Nobody understands. So existence, not real design. That's a big misunderstanding, at least for use of the neural nets. Don't talk about theoretical results. Rely on the theoretical result. You're talking about something good enough. Not really. Okay. So no art at all to me for this deep learning stuff, because they just a tuning job, only tuning. Okay. Hyperparameter tuning, trial error exercise. That's just for not for talented people like you sitting here. Okay. So you need to pursue the answer why and how to design, rather than you use the model because of the existence. Okay. To me, that'd be silly, no logic. So we need to understand more about this model and the learning algorithm. So that we can design the architecture, we understand how to make the model to perform steady, robust, and reliable, so with interpretability and explainability. Okay, that's what we need to do in machine learning. I show you example. Okay, so here just to do numerical function approximation. So that's in blue lines. Okay, that's why I show you this simple illustration just to let you realize machine learning, we have a long way to go. Okay, rather than the tools telling us something, don't trust these tools. Okay, so I ran this simply using MATLAB optimized software. Okay, try to we sampling from these blue lines. Then let's train use a MATLAB bifurcation, but here specific to find. Observe the impact of initial weights. How the initial weights will impact the learning process. Now, epoch 50 and 100 and 1,000, 2,000. Now you can tell. So these blue lines, that's original function to be approximated. Now this MATLAB output, neural nets. You can tell such a simple approximation task, but we have such a lousy performance. Neural nets can do everything. Maybe shocking you, right? People talking about success, they never talk knowledge. They are not interested in knowledge. They are interested in commercial, successful application. That's, I think, misleading, a lot of misleading media. Okay. To me, I think we need to understand this bifurcation is really not good enough. Say, we can change initial weights. We'll see how it works. We change it many times and then similar results. That's what we're talking about with Ivan with the paper talking about. So stability of the performance. Now, another from real data sets example. Let's further explore the stability bifurcation learning. Okay, so these 3 data sets from real industry, and then the group that's from testing data sets, 100 times trials. Then you observe, you'll see very unstable. Right. So that's the Ivan's paper talking about. So I fully understand what the paper is about. Very unstable. And then if we are concerned, the prediction performance, you can tell, do you think that's good enough? Of course. So the blue and ice, that came from our staff. Stochastic configuration network. So performance, right? Exactly, we do the same thing 100 times trials, but you look, this ISM perform with very, very lower error, but very stable. The performance is very stable. Okay, so that's about something piece of false in randomized learning over past 2 decades, even 3 decades. So that's our history for randomized learning. So this picture I just adopted from this publication in neural networks. Okay. It's a Bernard Weisel. Probably you young guys don't know. So this is famous guy from Stanford University. Okay, now I think over 80, retired professor. But he published a work, that's say 2013, published with maybe 3 postdoc. Okay, why I laughed? The reason is totally illogical thinking. I have to laugh. The foundation, no understanding at all. Let's read. Okay. So this architecture, this professor make a statement about ability and then some feature or characteristic of this kind of randomized learner. Okay. They talk about something like this. This machine learning is a neural nets. This layer, the weights, they can randomly setting without any concern about the data, independent of the data. Okay, first point. Second, they conclude this neural net model performance totally depends on last layer, the number and the weights. Do you think this is logical? They publish in Flag Journal Neural Network. That's a 2013 story. I sent an email to him. I challenged him. Do you think that's logical? And the second day, I received his response, this long email. And I sent him my code. He kept quiet until now. He understand he did totally wrong thing and published. I didn't make any comments paper about this. I think waste my time. Okay. Let this famous professor understand is not right. Okay. Let me give you some information about randomized learning because today I'm talking about stochastic configuration network. That's a class of randomized learner model. Okay, I developed, created. That's from David. I think Bloom. I think you know, probably from UK. So they talk about random RBF. So that means the center can be randomly assigned. Okay, whatever depends on the data or totally independent data. Okay, then they have a piece of work published online. You can read, you can download. I think we have something called random vector functional link. That's from Professor Paul, and then his postdoc from Russia. So I think Boris Igonik. Probably my pronunciation is wrong. Okay. Boris Igonik. Now this guy work in American but not academic. Always project research. Probably his English not good enough. In 1995, they published a piece of fundamental work results about randomized learning. Okay, so they proved mathematically this randomized expression they have universal approximation power in probability 1. Okay, so published in. And later on, from Germany, Jager published his very influential work. It's called echo state network. People talk too much about this. And now people turn to talk short-term memory model. Whatever, all of these, I think they have no math foundation. That's what we, I think with Ivan, we discussed. feature of them. All these randomized algorithms, so very data. That means design. Okay, open loop design. That's a control. Okay, so you can put the seeds, you can put the weights, random weights, just like you throw the seeds on the table. You have no any design, totally free. You are happy, but the resulting model can be very lousy. That's a consequence, right? So until 2017, I published with my student. We published a piece of work, Stochastic configuration network, and in this working area. That's why I keep talking about this in different conferences in China, overseas. I came back from Australia to China, that's 2020. I keep talking around the country because I believe this is something quite important. Totally change this illogical thinking. So every loop design. The random citing must be linked to this data. That's very logical. But people say, how we can make a link? So I propose that's today how I make the link. Indeed, so motivated, inspired by Ivan here. That's my life friend. I can't leave him, he can't leave me for the life. So that's why he invited me to be here to share my knowledge with you. And then probably I will be visiting a professor in Skoltech very soon. Okay. Now, information. The paper I'm talking about this. Okay. Now, pro algorithm totally play the words. Okay, play mine. Not really. I could. Another one. So I mentioned already. So reservoir computing, exactly same thing. All these random parameters here in reservoir units totally assigned random parameter without the data dependency relationship. Independent data of this size currently we developed in the past with one PhD student of mine. Last year graduated from Northeastern University. So we published 6 trans papers. We target solve this problem. Okay. But rather than state stuff. Okay. Still, we have theoretical work left. So if you guys are interested, you can contact me or Ivan. So let's work out. So get some milestone work at theoretical parts. Now, let's have a look at advances in randomized learning. Okay. What we have achieved so far. Of course, we published around 50 papers with these concepts, stochastic configuration network. Even now, still, the paper already cited, I think, over 800 times. About maybe 1 day, 2 days, I got another extra. I'm not talking about that. I'm just gave you the signal. People love it, and then they realize something extra, much more than what people talk about in the past. Okay. The same. I just 0.36 seconds. I can get this learning performance like this. Exactly, you couldn't tell the difference already. Still, maybe fresh in your memory, look at this. How many times? If you keep going, keep training, maybe go another 70 per second, but still doesn't work. You know. So this is a very interesting example. So, okay, 0.6 or even 0.4, whatever. That's a different level of machine learning exercise. Let's talk a little bit about architecture, about these of these stochastic configuration network. So MLP, multi-layer perception. So you know the right line we have the adjustable parameter, so we output weights, and then all these weights in the black lines. So that's randomly assigned. So which way assign of this one way to assign these random parameters. So what we do, we use this filter. That's what I propose. So I contribute to the machine learning. I think just this constraint. We call supervisory mechanism. Some days ago, sometimes I call the Wang's lemma, whatever. Okay, this is very important because the run and through the constraint. Okay, so that we can get these results very quickly. Okay. Now, I think I just show you what the fundamental result looks like. Under such constraint for the weights, we can conclude this convergence guaranteed. Guys, do you think learning, you can guarantee the learning performance tends to be 0? Have you seen these results in the past? For example, bipropagation, do you think deep learning, do you think you have such results on hand? I don't think so. In the, at least to me, I never see. Industry practice. Okay, so this is soft sensor model, grounding, just a soil. So it is. This and the floor and the water of each. I think we specify the size. So what's the percentage we have? Right. Okay. So that's what I have done. And then so far, I got a piece of work done as an industry product. So that's I have a partner from industry. Okay. You want if I think the time. Right? If people. Okay. Now, let's just look look at the results, comparing against these MLP and randomized model. So you can tell. So we use this mean square measure, and we use R correlation coefficient. So the training test, so our SN outperformed that. So this is industry exercise. Let people understand. That's what my goal is. Let the world understand. So people talking too much wrong things, especially for industry application. Totally no understanding. We have a much better solution over there, but people simply ignore. But I let the world make it the world. Okay. I think and that's a little bit near to you. So Xinjiang, so this is data model. And we have full circle voltage prediction, and we have automatic. So that's we have this. 3 minutes. Then of SN minus 3 T minus 2 as a feature of this. And then we have minus T plus 1, T plus 2. So 15 feature of this output. So because it's 5 times 3. So we train the neural nets with the data, many data, many samples. And then we get a result like this. The model results are amazing. People feel, from industry point of view, they can't believe such a high accuracy in prediction. That's called data modeling. Now, I think that's a simulation, not the real. But today, I show you the real thing. You look at this result. That's a real equipped our model in the system. System gave us the reports. All the data, detailed data here, you can read. Okay. So that's what we are working with the company, with real data sets. And then I think practice maybe more industries. But today, I came here, but that's why, Alex, you understand. I meet big bosses. Last night, this morning, too. Wow, they have a big garden, industry garden, big one, with 20 buildings at this level. I met him and discussed, and then I talked to them. That's what I have to work out some solution. Access is real industry. So that's what I'm doing. I think the last part, I will express my opinion as perspectives. Okay. What machine learning we really need to do. So as or masters, so in fact, what we need to do, contribute to the society with our scalability drives for the next generation of automation or intelligent manufacturing system. So scalability, you ask yourself, if you develop system or algorithm, they have a very good, strong scalability power. You can't, if billions, you cannot work. You develop the system with very strong scalability. The very, very basic needs from industry. As we are beginning, I already talked about this point. So speedy learning, dating, that's for industry. A more intelligent solution age framework. So that's, I think, last night I talked to the boss. His key area, that's distributed AI. And I talked to him, what distributed AI, what you need from academic. He say, I need lightweight algorithm model, the fast adaptation learning algorithm. I say, okay, I'm the best person in the world. So that's the guy, very happy. He take me, anytime he has a big building and we can use. Totally for free. So that's a big boss. They have a philosophy. They understand who I am. The guys, if you really one day you're interested in working in China, you contact me, I'll help you. Okay. Try to combine, integrate all this stuff together to make more I think data, high quality data, they said all these exercise from industry AI, we need not only algorithm, silos. I think the data science with a high quality, I think that's a very key to your success. Very important. Now, summarize something about this precise industry. Okay, so what it is, indeed, we have these three components for industry, but so we have a device, we have material, we have precise parameter, so that you can play around tuning, optimizing, right? So that's what we are. We can't change much about device. You can't change, you choose the material, the raw material you want to change. We have no such a power, okay? Mining material, what do you want to do? Rubber material, what do you want to do? Manufacturing, we import from somewhere. That's not our business. Our business can on the optimization. That's what we are doing. That's AI will be applied here. With this machine learning, so modeling, optimization, and intelligent control. So in the end, all these factories, manufacturers, they are interested in control something. So control something, they aim to save energy, to make the products more stable, high product, right? So these are three pursuit. That's, I think, industry, they are interested. Okay. I think as a core support, technical support to solve this industry AI problem, we need first lightweight learning model. That's very, very important. I think in the future, the competition between America and China, I think, goes to these parts. Don't talk about others, something else. That's totally nothing related to the industry AI. So industry AI must be talking about lightweights. So to this age, computing, system scalability, fast adaptation, everything. That's from lightweights model. Okay. Second, time optimization. Evolutional computation. We have the good general transaction evolution computation. But do you think any paper talking about real time? They're talking about maybe take 1 year, 1 month, why optimize something, but don't talk about industry application, okay? Far, far away. So I believe, even I'm not myself doing this area, this topic, but I truly believe go randomized approach. The randomized, very good stuff. Okay. Control, so here PID and MPC, model predictive control. PID tuning parameter of the PID. So that's already everyone knows. Okay, but still is the future is a core technology techniques for solving industry problem. Okay. And I want here today. I think learning plus physics. That's what people talking about. In the first I mentioned, your predictive output should conform with the physical law. How comes? You ask this question. How comes? Do you think a data-driven approach can produce such a model? So your prediction will conform with the physical law. It's impossible. So that's, I think, we need more and more academic and devoted in this area. Okay. So people teach a lot in nature science and maybe computation physics. The physics review so many prestigious journals. They keep publishing this in PIN, so physics informed neural nets. Not enough. Okay. I think in May we set up the lab, and then Vito already gave a very good speech about this knowledge-based, so knowledge-informed machine learning. If you just take your time to think about this. For example, your output is monotonic with respect to specific inputs. How you can make your predictive model can perform like this? How? And then you need a model training, learning very fast, and then the predict output conform the physical law, and then lightweight, and you can explain the result. How? That's why at this age I'm still very energetic, high passion, because I know this is exciting. It's useful stuff to the world, to industry. Okay. A key reference. So in the last few years, and then Xi Kai-xie already passed, I think, 2 or 3 years ago at 98. PhD academician Professor Tianyou Cai. In China, everyone knows. So he's the big contributor for industry AI and automation. He's a leading professor over the nation. That's this guy sitting Ivan, Turkey. my lifetime friends. Okay. So that's why you guys are from Russia. I'm very happy to meet you here. Okay, and will come and came to visit me in Qingdao. Okay. Thank you. That's it.
Questions?
Thank you very much. So, Professor Wang, thank you very much for the brilliant talk. Of course, with the passion as always. So, I got your message. I think I share those ideas. Now, I want to know your opinion about the possibility of using your stuff for large language models. Do you think we can build LLMs with the stochastic integration stuff in the same way? Thank you.
Thank you very much. It's a good, very interesting and good question. Okay, first of all, last night we discussed this problem based on TikTok. Okay, about not very intelligent implementation, but very intelligent is advanced technology as well. He asked me, Professor Wang, do you think that stuff still can do something else? That means you want to apply this maybe for some large scale problem, given energy conservation. I said probably we can try. If it works, it works. Or how good if this stochastic configuration network is the best candidate to beat this, for example, large model. Nobody knows because nobody tried. Now, to my all understanding, everything is possible because propagation driven based algorithm, whatever, just maybe deep model, convolution, whatever, that's a parameter tuning, right? Pause back, pause back. I don't think the philosophy is right. The learning philosophy itself totally conflict with the file learning system. But this randomized, stochastic, at least a better solution. So we can try. Let's try. Please.
Yeah, once again, thank you for your lecture. I believe that this direction is quite interesting. Like another, I believe, expert has asked question related to generalization to large language models, and this is one point. The second point is that many new architectures or methods like Kolmogorov hard networks, like Mambas and other things that that claim that they will that they will replace either transformer or multi-layer perceptrons. They failed because of the modern kernels and computational resources are optimized for some specific operations. For instance, like we have like VLLM, we have other kernels. Do you believe that like the methods and architectures that you are proposing does not have such gap, and in terms of computations, we will not struggle and achieve the same performance as in multi-layered perceptrons, for instance? Thank you.
All right, okay. I roughly understand, get your points, okay? I think my opinion for this, you're asking the problem is, I think a transformer something, this existing quite well known and commercially used model. For example, they build attention mechanism in the learning. That's talking about the feature selection, extraction, right? I think let's go this way. If we use whatever deep learning stuff, all these including transformer, as a feature extractor, and then we, after getting this extraction, this feature, in the new feature space, let's make a comparison. Okay.
Okay, thank you.
So that's I think you can find a solution. For example, computer vision application. I don't think these you use the single ICN stuff couldn't get a good solution. Because you think this way, they have 1 million parameters. We have 1,000 parameters. How you can make a comparison against, right? Because
yeah, so
they are so complicated. Most of them, 80% job goes to feature extraction rather than, approximation.
Yeah, so you believe that like you have a smaller amount of parameters and better generalizations. That's why it's A, impossible to compare, B, you will not lose in computations because your models are generally smaller and competitive in terms of performance. Am I understood this correctly?
Yeah. I think we can apply deep learning stuff for feature extraction and plus ICN. That's the ideal approach.
Yeah, okay, thank you.
That's what I believe.
Thank you for your lecture. It was interesting. During your lecture, you mentioned that implementation of real-time optimization in industrial setting is not feasible nowadays, but what the achievement in the academia in this research branch, which areas are the most promising to implement in the industry and how, when it's expected?
Yeah. It's a very promising direction for industry AI. Okay, I mean, you're talking about real-time optimization, right? For industry setting. That's so far, I think a group of people around the world, they are trying to solve the problem. Especially my PhD supervisor, just to say, Professor Tai, his group have a young academic brother, so they are trying very hard to solve this problem. I think that's based on industry individual scenario, and then you find some formulated problem, and then you get a solution, right? Rather than simply mimic human or maybe animal group behavior, you try to optimize something. I don't think so. You have to refer the industry setting. So this problem formulation is a key. But methodology, I believe randomize is a solution. Randomize.
Thanks.
You can try, because I'm not working, I can't tell you too much in details because I'm not working in optimization problem. I'm working in, I think, regression using neural nets, randomized neural nets. That's Skoltech I developed in this past decade. Right. But it's very important for industry. Industry AI, we have to address this real time. Otherwise, it's meaningless. You can't wait maybe 5 hours or even 10 minutes. You got your tuning your parameters. That's a key parameter in your system. Maybe can result disaster. You can wait. You can't wait. Thank you for your question.
Thank you for your answer.
Thank you so much, guys.